right. Let me get the lights adjusted, get my little clicker plugged in. I know I must have. Okay, all right. Okay, let's get started. I don't know if there's like a traffic jam or something, but like, was the first celebration that bad? Like, my goodness. I'll wait a little bit before I pass the sign-in sheet around because I'm such a nice guy. Okay, so let's take care of some housekeeping. Okay, so first off, TA is still working on grading homework number 3, and I have yet to grade exam number 1. My goal is to try and get that graded throughout the weekend. Come on. Next contestant on The Price is Right. What I will probably do, and I haven't made up my mind. I will see how class goes today, but I might show you the solution to the exam today. And normally I don't do that until I have the exam grades to give back to you. But my schedule for the next little bit is anything but normal. So let's talk about that. So if you remember in the beginning of the semester, I told you right around the beginning of October that my schedule was going to get a little weird. Well, guess what? Next week is the beginning of October. My wife just hit 39 weeks today, so now it's the waiting game. So let's talk about that. Okay, if you go to the syllabus, okay, if you look at the syllabus, you will see that on October 4th, I have what's called a makeup day. I put it on October 4th because that was her due date. But I don't know when that's going to happen. Okay, so here's what I've got here on the slide. I've got the series of topics that we are going to talk about from now until exam 2. Okay, but I've just got them in order. Okay, we're going to have a break in there someday. I can almost guarantee it. We're going to have a day where we're not meeting. Okay. I don't know when. I have no idea. So here's a couple things that I wanted to bring up to you because when in terms of scheduling, you know, we think, well, that's probably going to start to happen now. So number 1, okay, if you all receive an email from a guy named Patrick Quinlan, that's not spam, okay? How many of you had me for 103? No, that's the freshman seminar, the big one. Okay, so a couple of you have me. So you know that I used to use Patrick to take attendance for the class. So Patrick, what I did is I gave Patrick the email roster for everybody. And I told him, I said, I might send him a text and say, could you just email structural analysis and say, ain't going to make it, okay? So if you receive an email from Patrick, it's not spam. Just make sure that you pay attention to it. Somewhere, one of these days, we're going to push down. Maybe it's October 4th, maybe it's later, I don't know, we'll see. But just be patient with me on that. It's also possible that I have an exam, one of these topics is an online lecture where I just post a video online and say just watch that. So just be aware of that. Now in terms of homework and assignments, you all don't have anything on your plate right now, so you're good there. And as for future assignments, I have an assignment that's going to be assigned on Tuesday that's going to show up on Blackboard, but it's not due for a while. When's the due date on it? I think it's October 16th. So it's not due for a good little while. And it's actually a pretty straightforward assignment. There's one section property problem and a few shear and moment diagrams, and they're pretty straightforward. So the shear and moment diagrams that we do in here are really, really simple. For those of you that are in structural analysis, you're going to sleep through that homework. I'm not going to lie. Yeah, I mean, you all are working on one right now that is infinitely more complex than the one that we do in here. So yeah, so just be patient with me. I'll try and keep you posted. Sound good? All right. And like I said, I might go through the solution with you at the end of class. We'll see where we get today, because there are some things we do need to talk about today. So just so you are aware, today might feel a little bit like movie time, and a little bit, we are going to do some math here later. I apologize that right after the exam, we're going to break out the the C word again and introduce a little bit of calculus, but it is pretty straightforward. So with that, let's just go ahead and get started. So we're in Exam 2 territory. This is brand new stuff. This is stuff that we sort of mentioned right at the end of our lecture topics last time, but this is where we're sort of going to dig into this a little bit. And so this might have been a wonderful first lecture for this class, but honestly, I'm a little impatient, and I'm like, damn it, let's just get right into the stresses and strains and all of that. But let me explain sort of what this lecture is about and what we're talking about. I almost just sort of want to go back to square one. I mean, we all know, I think, by now why we're in this class. I mean, and beyond just degree work said we had to check this little box to get our degree. There are some very specific skills and some very specific concepts that you learn in here that you will use throughout your engineering career. So this class carries with it a significant importance. I mean, the concept of stress is something that you will use throughout your engineering career. However, one of the things about stress in general is that stress is a function really of two things. Number one, it's a function of your member or your structure's response to given loads. And so a lot of that comes from statics. You know, you sum forces in some moments to determine what's the shear right here, or what's the moment right here, or what's the axial load in this member, how much torsion is this thing, so on and so forth. And by and large, that comes from statics, okay? But stresses also come from section properties, from geometric properties of areas, okay? If I take a samurai sword or a lightsaber through a given bar or circular shaft or beam or whatever, I'm going to be seeing a shape. You know, if I'm looking at a building, like how many of y'all have seen the new pharmacy complex being constructed on Hal Greer? Okay, so if I take a samurai sword through some of those beams, the contractor's not going to be very happy with me. But if I do, I'm going to see an eye shape. You know, a flange, a web. I'm going to see that shape. Well, that shape has certain numerical properties associated with it. For instance, it has a cross-sectional area. How big is that area, and so on and so forth. Now, by now, we should recognize that some of those values and some of those properties are really important to us. For instance, we need to know the cross-sectional area of that I-beam. If there's ever an axial load applied to it, well, P over A will tell us the normal stress. And then we use that normal stress to determine whether or not the member is sufficient, and so on and so forth. Well, geometric properties or section properties in and of themselves are an incredibly important topic to this class. We're not really talking about stresses and strains and things like that. What we're talking about are just basic properties of areas. Here's a shape, and what do we know about that shape, okay? So we need to sort of take a step back and just talk about that, just talk about shapes, talk about the properties that we can derive. We've already used a couple of them. We know what cross-sectional areas are. We know what J is, okay, because we use that for circular shafts, but there's a whole host of other ones that we need to deal with. So this lecture is going to seem a little basic, but you're going to see how some of these properties that we utilize are incredibly valuable. Like I said, you all know how to compute area. Like from a calculus perspective, you all knew how to do that before we got here. You know, if you have some curve, how do you determine the area under the curve? Well, it's the integral. Integral from, you know, your left limit to your right limit, and so on and so forth. Ultimately, what I'm going to be driving at is a particular section property that's new, something that I know we haven't talked about in here. You may have mentioned it in statics. I'm not sure. In statics, were you ever exposed to a moment of inertia or a second moment of area? Did that concept ever pop up? Physics? Okay, all right. You might, yeah, so it makes sense that you saw it in physics. You might have seen it in physics from a mass moment of inertia perspective. In here, where we use that concept is a little different. It basically relates to a big concept that we as engineers deal with, and that's bending. So moments of inertia are going to play a very big role there, and so that's sort of where I'm headed. But I'm going to take it one step at a time, and I'm going to start off with area. So we know area, just the integral of from a to b of f of x dx, you know, straightforward. Now let's go back, way back to Math 229 to Calc 1. When you compute an integral, remember what an integral is. It's basically a sum, right? Remember, you're divvying up that region into these little itty-bitty rectangles that are f of x wide and or f of x tall and dx wide, and then you're summing those up over that region, right? So what I'm going to do, just for a little bit of shorthand in these lectures, is I'm going to introduce a term called dA, okay? And so dA, for instance, for this, is going to be the area of that little itty-bitty rectangle. That's dx wide and f of x tall. So that dA term is f of x dx. And so when I integrate, let's say, over that area, I'm just summing up those little rectangles. And so if you're wondering what the heck is dA, that's what I'm talking about. Okay? Does that make sense? Okay. All right. Now, I also want to introduce a term that might be new, and this is a moment of area. Now, you all have dealt with moments before, so I think this is a pretty straightforward concept, but I don't know if you have heard it referred to in this fashion, okay? The first moment of area, instead of computing the integral of just dA, or the integral of the function, you know, from a to b, we're taking the integral of the function times x. So it's sort of like that area times a distance, okay? So if we're talking about moments about, let's say, about the y-axis, well, we're basically saying, well, how far is this little strip of area from the y-axis? Well, how far is it from this point to here? Well, it's x, okay? So that first moment is just the area times x. So if the area integral is just the integral of dA, the first moment is the integral of x dA, okay? And if there is a first moment that we can compute, there's also a second moment of area that we can compute. So we could, instead of just taking the integral of x dA, we could take the integral of x squared dA. And I'm sure some of you are like, sure, great, who cares? Like, wonderful, just make the integrals more complicated, why don't you? But what I'm getting at, each of those integrals has a specific purpose in our world, okay? And a little bit of a spoiler alert, this integral right here, this first one, a first moment, is very useful if you want to determine a centroid, okay? And so that is a term I am pretty sure everybody in here is familiar with, right? So you could sort of see, I'm not just introducing this just for the heck of it, they do have specific uses, okay? So to summarize what I've got so far, I've got an area, which would be the integral of just dA, a first moment, which would be the integral of x dA, and then a second moment of area, which is the integral of x squared dA, okay? So everybody okay with that? Now, again, the big question is, who cares? Why are they useful? Like, how are we going to use these values? Okay? All right. The first moment of area can be used to determine the centroid. Okay? So the idea behind determining a centroid and the reason why that is so valuable is we say, all right, our first moment of area, we know our first moment of area is the integral of x dA. Well, I would like to compute that in a little bit more of an easier fashion. Maybe there's some special distance, some x bar, whereas if I take this entire area and multiply it by that moment on that x bar, that it would be equivalent to this entire area. Does that value exist? Yes, it's called the centroid. So x bar for that shape would be the first moment divided by the area. So the integral of x dA divided by the integral of dA, okay? And so that's where this term is coming from. And similarly, we could determine y bar by just determining the integral of y dA divided by the area, okay? And so that is something I think you all should have been exposed to before. You might not have seen it in an integral fashion, which you probably remember is something like the sum of ax divided by the sum of a. Have y'all remember that? Well, remember, what is an integral? It's a sum, you know. So an integral is dealing with centroids in a little bit more of a continuous fashion, whereas what you did with centroids and simple shapes probably in something like statics, and we're going to revisit that in here, is dealing with it from a discrete fashion. If I know what the properties of a rectangle are, and let's say if I know how to determine the centroid of a rectangle, well, what's an I-beam? It's just a bunch of rectangles. So I don't need to break out the calculus for something like that. We're going to do both just to make sure everybody's familiar with it. Now, just from a straightforward perspective, what is a centroid? Well, a centroid is basically the point at which the moment caused by that shape is 0. So in other words, like if I had this toy bird, if you look at the way its mass is distributed, it seems a little weird, but actually the centroid of that bird's mass is actually right there on its beak. So if you place that toy bird right there on the tip of your finger, it will not generate any moment. It won't turn or do this, like you have to balance it a little bit. But in the end, the moment generated by that shape is 0. Now, of course, it has a force. It's acting down. I mean, if your finger wasn't there, that bird would fall and hit the ground. But it's not twisting and turning. And that's sort of what the centroid is. One other very important point to keep in mind, it is very possible for the centroid of a shape to not be on the shape at all. Okay? Where is the centroid on a donut? Right in the middle. So it's not on the shape. Okay? That's possible as well. And so from an engineering perspective, sometimes you might have to deal with that. So just something to keep in mind. Now, like I said, this is something that you're probably a little more familiar with. Remember, an integral is just summing up an area. So if you know the centroids and the areas of basic shapes, you can then determine the centroid of a composite shape. In other words, a shape made up of a bunch of simple shapes by just sum of AX over sum of A, or sum of AY over sum of A. Now, one thing to keep in mind, there is a table in the appendix, or there's an appendix in your textbook. I think it's in the notes. Quite frankly, I can't remember. I want to say it's like Appendix B or something like that, that literally lists simple shapes. Like if you have a triangle, here's the area, here's the moment of inertia, here's the centroid, and so on and so forth. And so that might be a pretty valuable resource. And I believe I also posted a PDF of that appendix on Blackboard. I'm pretty sure it's on there as well. Now, the centroid is actually a very important relationship for bending. When you bend an element, when we start to develop bending theory, which is something we'll talk about later, the centroid is where bending stresses, like if all you're doing is applying bending, it's where bending stresses are 0, okay? It's also where torsional stresses are 0, and we've actually kind of already seen that. If you have a circular shape, where is the centroid? It's right in the middle of it, right? Well, if you apply torsion, where are the largest stresses? They're along the wall of the shaft. Well, where are the lowest stresses? In the middle. There are no torsional stresses in the center. So centroid has already sort of crept up in an indirect way, and it's going to creep up in a very direct way when we deal with bending. So the centroid is going to be pretty important to us a little later. Now, that's where that first moment of area becomes valuable. So I'm going to skip back a little bit, just so everybody's aware. So remember, we had an area, we had a first moment of area, and we have a second moment of area. We haven't talked about that second moment of area. Well, that second moment of area is a very, very, very popular or a very valuable and useful measure of a given section, okay? We usually don't call it the second moment of area. We have a very specific name for it. We call it the moment of inertia. Now, just so that I'm being, specific in my language, this is a little different from what you've dealt with in dynamics. Dynamics, you've probably heard of or physics, you've probably heard of a mass moment of inertia. What we're dealing with is an area moment of inertia. It's just referring to a distribution of the shape's area. But I'll be honest with you, I'm probably never going to call it an area moment of inertia, and I'm probably never going to call it a second moment of area. I'm just going to call it a moment of inertia in here. So if you're wondering, language and terminology, I'm just going to use moment of inertia. So we have moment of inertia values about the x-axis and about the y-axis. Now, if you're trying to determine the meaning of the math, sometimes it's a little complicated if you're trying to investigate the integral. But I'm an engineer, and I like to keep things pretty straightforward and simple. If you're wondering how a moment of inertia plays into engineering, why do we care about moments of inertia, I'd like to introduce you to this example, and I think I kind of mentioned this right before we went into exam territory. I have here a framed system of floor joists for use as an outdoor flooring system. So the idea is you'd place planks or plywood or something like that on top of this, and it would serve as some sort of floor or platform system. Now, if I look at the joists, notice how the joists are sort of standing upright, You know, I've got them like this. Why do I stand them upright as opposed to like this? Like, why don't I just lay the floor joists flat? Sorry, why don't I just lay them flat? Well, if you've ever messed around with lumber or even a yardstick or something like that, I mean, if you had a yardstick in your hand, you know there's sort of a strong direction of the yardstick and a weak direction of the yardstick. In other words, one way of bending it, the yardstick is really flimsy. You know, you bend it really easy. But the other way, like, you can't do that. It's much stiffer. It's much stronger in that direction, right? The reason why, if you want to get into the numbers and the theory, the reason why is because the moment of inertia about that axis is much larger, okay? The moment of inertia is essentially a representation of bending stiffness. The higher the moment of inertia, the harder it is to get that beam to flex, okay? And moment of inertia values change depending upon the orientation. This wooden joist would have a very strong moment of inertia if it's faced, or a very large moment of inertia if it's faced this way. It has a very low moment of inertia if it's faced this way. If you ever hear me in this course refer to the strong axis or the weak axis, that's what I'm talking about. I'm talking about the way that a given beam should be oriented in order to generate its maximum stiffness. Now, for an I-beam or a 2x4 or 2x6 or something like that, it's pretty simple. Face it the long way up. And so it's usually easy to determine which is your strong axis and which is your weak axis. However, if you have a shape, let's say, that's like this, which is very common in mechanical engineering applications and what have you, and even civil engineering applications, you can have some box girder cross sections or some reinforced concrete cross sections where it's not that straightforward to determine which is the strong axis. You calculate it. So we would determine a moment of inertia about this axis and a moment of inertia about that axis, and then we would, you know, break that down accordingly. Does that make sense? Everybody okay with that? All right.
So, like on that, it's because the moment of inertia is related to the square of the thickness that is perpendicular to the load.
That's a good question, and so you said is because it's related to the square of the thickness. Actually, so conceptually you're right, but it's actually not the square, it's the cube. When you calculate, so for instance, spoiler alert. Yeah, so spoiler alert, for a rectangle, the centroidal moment of inertia is BH cubed over 12, okay? So that's sort of a common formula for you. So if you're looking at it in this direction, this is B and that's H. So you're taking BH cubed. So to take the larger value, cube it, you get a much larger value. Whereas here, BH cubed, you have a tiny h. So the h, where the h is smaller, you cube it, you get a much smaller value. So that makes sense? So you're right, but it's a cube, it's not a square. So sound good? This is good stuff. Okay. So what I want to do is I want to go through a simple example. Okay? This is real simple. All right? I'm doing a rectangle because the properties are really straightforward. But I want to illustrate to you how the math works. And then we're going to do a problem that isn't so simple, where the math is a little more complicated. So I have a rectangle, and I want to integrate to determine its area, its centroid, and so on and so forth. Now, I'm using the rectangle because a lot of this is pretty simple. Guys, what's the area of a rectangle if it's b wide and h tall? B times h, yeah. So when we perform our integral, we better get that or I'm doing something wrong, right? Where's the centroid? From here to here, how far is it to get to the centroid? B over 2. And here it's h over 2, right? So let's see if that works, okay? So if we observe this shape from a mathematical standpoint, okay, our y function, our f of x, is a constant. It's just f of x equals h. So what we're doing is we have a shape. So how would we define this shape mathematically? Well, it would be a shape bounded by the curve f of x equals h, and that would be bounded from x equals 0 to x equals b, right? So when we integrate, we'd be following those parameters. So let's just sort of follow along and let's see what happens. So first off, to compute the area, one thing to keep in mind is that our little differential slice, we can define it two different ways, okay? I could define a differential slice that's, let's say, dx wide and h tall Or I could define a differential slice that's b wide and dy tall. Now, you might go, why would you do that? Well, if you have to determine moments of inertia about the x-axis and the y-axis, having those slices go either way is actually kind of important, and we're going to have an example later where it's pretty necessary. So if I use, let's say, the first one to compute the area, I propose what I'm doing is I'm summing up these slices from x equals 0 to x equals b. So I'm integrating from x equals 0 to x equals b h dx. So what's the integral of h? It's hx. Plug in the top number minus plug in the bottom number, and that's what I get, right? I can leave this up here if y'all want. You want me to wait a little bit? Yeah, sure, no, that's fine, that's fine. All right. So far, so good? Okay, so that's an area, okay? Now, let me show you this. What if we did it the other way? You don't have to write this down if you want, but I just want to show you. Well, if we integrated in this direction, we'd be integrating with respect to y. So we'd be integrating this from y equals 0 to y equals b. And so the integral of b with respect to y, that would be by evaluated from, plug in the top number minus plug in the bottom number, and you get bh. Everybody okay with that? I can leave this up if y'all want to write that down. It's okay. Don't worry. We're going to have an example that's a little more intense here in a little bit. Okay. Now, if we're determining centroids, okay, we got to be careful. Okay. So you'll see what I'm doing here in a second. So just bear with me. I'm doing the x-axis first. So let's do our first moment of area about the x-axis. So I'm going to integrate this xdA. So when I say can't match the axis, what I mean is if I'm integrating, let's say, xdA, make sure that my expression for dA also is a function of x. You don't want to use b dy because then you'd be having two different variables and it would be kind of messy. Don't worry, we'll explore that here in a second. But if I integrate with respect to x, so I integrate h dx, so what is the integral of x? Well, it's x squared over 2. Evaluate, plug in the top number minus plug in the bottom number, plug and chug, and I get this, b squared h over 2. So that's the first moment of area, okay? Does that make sense? I can leave this up here if y'all need a minute. Y'all good? Okay, so if I do y, so here's what I was saying with match the axis. See, remember we had two different definitions for dA? Make sure that you're matching. So this is y, that's y. So integrate, so on and so forth. You get a very similar term when it's all evaluated, but instead of it's being b squared h, it's bh squared, okay? Now that's your first moment of area. How do you determine the centroid? Well, you take that first moment and you divide it by the area. So what is this divided by the area? It's b over 2. What is this divided by the area? It's h over 2. Where did we say the centroid of a rectangle was? b over 2, h over 2, right? Pretty straightforward, right? The point is that for a rectangle, it's simple. What if it's not a rectangle? What if it's a shape that's much more involved and much more complicated? Well, if it's built up of a bunch of simple shapes, don't break out the calculus. But what we're going to do here in a second, yeah, that's a little more rigorous. Okay? So far, so good? All right. Now, for moments of inertia, the same rules apply. Now, what I'm going to do is I'm going to integrate about the x-axis. Okay? So I integrate y squared dA. Now, some of you might be looking ahead and you're going, wait a minute, I thought Dr. Mike said bh cubed over 12. Why does that say bh cubed over 3? We're going to get to that. Don't worry. I promise. All right? Now, so I'm going to integrate y squared dA. So what do we have? So we're integrating y squared. Again, remember, match the axes, so b dy. We're integrating from y equals 0 to y equals h. And at that point, this should just be a Calc 1 problem. So integrate y squared. What's the integral of y squared? Y cubed over 3, right? From, plug in the top number minus plug in the bottom number, and you get bh cubed over 3. And you're going to get a similar expression for Iy. Instead of it being bh cubed over 3, it's going to be b cubed h over 3. It's just flipping the numbers. Now, you can follow the math, and you'll see you'll get the same thing. Okay? Everybody okay with this? All right. Now, if you're okay with that, what we're going to do is an example that's a little more tricky, a little more complicated. Okay? Now, we're going to take our time with this because the math is not hard, but I just want to make sure that everybody's following with what we're doing. And then afterwards, you're like, wait a minute, what about that bh cubed over 12? Did Dr. Mike forget that? No, I didn't forget that, so we will talk about that later, okay? Oh, and it's Appendix E. It's not Appendix B, so whoops. But I think, correct me if I'm wrong, but I believe there's a PDF on Blackboard of Appendix E, and it's just moments of inertia of basic shapes. But we'll talk about that here in a second. Okay, let's get right to it. Okay, so I have a shape that is bounded from x equals 0 to x equals a, and it's not a rectangle. We have a parabola. This is y equals kx squared. We're going to determine what that k is first. But we're going to try and determine some properties of this shape. Let's see if we can figure this out. All right. All right, so here's the shape. And our curve looks something like that. This is x equals a. This is x equals 0. This is y equals b. All right? And so what we're determining are the properties of that area, right? And so the curve is y equals kx squared. So it's a parabola, right? Okay, so the first thing I'm going to do is I'm going to determine k. All right? And the way that I'm going to do that is this. What are the values, or what are the coordinates of that point right there? AB, right? A comma B. All right, let me move this down a little bit. There we go. So we have y equals kx squared. So if that's the case, would you agree that that's the case? Just plug in B and plug in A, right? So therefore, K equals B over A squared, or Y equals B over A squared X squared. Would you agree with that? Any questions? Now, if you're okay with that, then what I want to do now is, before we start breaking out these integrals, I want to determine some differential elements of area. In other words, let's figure out what's going on with those DAs. If I know what DA is for, let's say, with respect to the x-axis, or DA with respect to the y-axis, the rest of this is just chugging out some basic integrals, okay? So the first thing that we will do is let's deal with respect to the x-axis, okay? So here's what I mean by that, okay? It might seem a little backwards, but bear with me. So here's our curve, right? All right. What we're talking about is this. So here's our curve and here's our area. What I want to know is what is the area of that rectangle. Okay, and you're going, well, wait a minute. It's with respect to the x-axis. Why is it going up and down? Shouldn't that be the y-axis? Well, no, because how far is it from here? That's x. Okay? So, here's what I propose. How wide is that? It's dx. How tall is it? It's y. So watch this. I propose that dA in this instance is y dx, which is here. I'll write like this. Here, let me do this. I propose that. In other words, that would be the expression for a differential area, a differential element of area with respect to x. Okay? And then all we have to do is integrate that, let's say, from x equals 0 to x equals what? A, to determine areas, moments, what have you. Sound good? Yes, sir. That's a great question. And so the question was, is x going to the inside or to the outside? And what I'm going to say is it doesn't matter, okay? Because here's the thing. You're assuming, and that's a great question, okay? When you ask that question, you're assuming that dx has some meaningful width. Remember, dx, so it really doesn't matter. So, yeah. So what I would say is it's going to the middle of it. So, all right. Sound good? All right. I know some mathematician out there is going to yell at me, but that doesn't matter. Okay. Now, with respect to the y-axis, okay, let's take a look at this. All right. So here's my curve. All right. Looks like that. Okay. And here's what we're doing. What we're doing in this instance is we're basically determining the area of this. Would you agree? Okay. All right. So, let's do a couple things right off the bat. How tall is this rectangle? dy. Now, how tall is it from the axis? That's y, right? And so ultimately what we're going to do is we're going to integrate from y equals 0 to y equals b, right? Okay. Now, how wide is this rectangle? Say that again? He's exactly right, okay? Remember, this point here on the curve, this point here where the rectangle and the curve intersect, okay, this distance right here is A, okay? That's A. Or no, sorry, I got that backwards. This is X, this is A, right? So how do you determine this? A minus X, right? Think. If this is 5 feet, and that's 2 feet, how do you determine this? 5 minus 2, okay? Does that make sense? So bigger one minus the small one. Okay. So I propose that dA in this instance is A minus X dy. But the problem is we still have this pesky x in here, okay? The problem is that x is still there. Remember, we want this to be just with respect to y. So how do I handle that? Well, let's go back to the function. Would you agree that y equals b over a squared x squared? Would you agree with that? So would you agree that a squared over by equals x squared? Just flip and multiply. So how do you determine x? Well, I propose that x is a over the square root of b, and then it's the square root of y, right? Now, what I'm going to do here is this. I'm going to write this as y to the 1/2, okay? Now, you can write square root of y. You can write y to the 1/2. There's a reason why I'm writing it separately, and the main reason is I want to indicate that power when I integrate, okay? So, because you might not remember, because I've done this a number of times. I'll have students that don't remember what the integral of the square root of x is, but they do remember what the integral of x to the 1/2 is, because they remember the power rule. So that's why I did that. Okay. So therefore, I propose then that dA is, what do we have? A minus a over the square root of b y to the 1/2 dy. Would you agree with that? Not too bad, right? Okay. There is a way of checking if these two values are compatible, okay? One way of checking if these two are compatible is to integrate both of them. If I integrate this, that'll give me the area, right? If I integrate this, that'll give me the area. Better be the same thing, right? Because it's the same shape. So let's see if that works. All right. Does everybody have all this? Do I need to leave it up here for a second? Okay. Okay. So remember, we have a dA. So recall. We have dA is b over a squared x dx, and then we also have dA is a minus a over the square root of b y to the 1/2 dy. Just wanted to rewrite that so that I had it on the screen. You didn't have to rewrite it. Okay. Oh, it was x squared. Yeah. That was a typo. Yep, x squared. Sorry. Okay. So let's look at area. Remember, area is just the integral of dA. So let's deal with respect to the x-axis. I think that's the easier one. So area is the integral over the area, which is, now here's what I'm going to do. I'm going to integrate, and we're integrating from x equals 0 to x equals a this. What do you think? Is that something that you could carry out on your own? I would hope. I'm going to go through this a little fast. Tell me if I'm going too fast. So I'm integrating with respect to x. So everything else is a constant. So pull that out. And I'm integrating x squared dx. Now what's the integral of x squared? There we go. So x cubed over 3. That's from x equals 0 to x equals a. And then, so pull out everything that's a constant. So b over 3a squared. And then plug in the top number minus plug in the bottom number. So I'm getting a cubed b over 3a squared. So I propose that the area is ab over 3. Would you agree with that? It's not too bad, right? Now, if you're okay with that, then let's do the next one to see if we get the same thing. It's a verification that our formulation is correct. Okay? So in this instance, what we're doing is we're still integrating over that area, but we're integrating from y equals 0 to y equals b of I forgot my parentheses. Of that. Okay? Now, I got two integrals, right? So if I got two integrals, I'm going to split them up. Okay? I'm also going to factor out all the constants. So forgive me. So let me know if this is too fast. So I'm going to say that this is the a times the integral of y equals 0 to y equals b of dy minus a over the square root of b times the integral of y equals 0 to y equals b of y to the 1/2 dy. Was that too fast? Okay. So the first one, we have a times the integral of dy, which is just going to be, there we go, from y equals 0 to y equals b minus a over the square root of b times what? 2/3? Yes, yeah, y to the 3/2 over 3/2, so yeah, so 2/3. So 2/3 y to the 3/2. I thought you were saying the exponent was 2/3. I was like, and that's from y equals 0 to y equals b. So handle each of these one at a time. So a, and then plug in the top number minus plug in the bottom number, minus, pull out all your constants. Then what do we have? We have b to the 3/2 minus 0 to the 3/2. Everybody okay with that? All right. So over here on the left, we just have AB. But what do we have over here? We have 2A over 3B, and all we're going to have is B to the 3/2, right? Well, I propose that B to the 3/2, or no, sorry, whoop, I forgot my square root of B. I propose that B to the 3/2 is just B square root of B. So the square root of B's cancel, and I get AB minus 2AB over 3. AB minus 2/3 of AB is 1/3 of AB. So we got the same answer. What's that? No, what? Where? Well, no, remember, this is 3 over 3. So that's a full minus 2/3. Yep. If that was AB over 3 minus 2AB over 3, then it would be negative, yeah. So that matched what we got up here. What do you think? Sound good? All right. Tell you what. Would you like it if I decided to hold out on the, illustration of all this calculus and we'll just lay out the integrals? Like, I get the feeling you all can do Calc 1. Is that okay? All right. So, first off, does everybody have all this, or do you need a little bit? Okay. All right. So, here's what I'm going to do. All right. Let's look at our first moments of area. Okay? So, the first thing I want to do is compute the integral of x dA. Okay? And so, what that's going to be is the integral from x equals 0 to x equals a of x times b over a squared x squared dx. Would you agree with that? You agree with that? Okay. Now, would you be fine if I just told you that that ends up being that? Like, do we need to carry it out, or do you believe me? Like, we can carry it out. Okay. So, that's that one. Now, how about this one? This one is going to be the integral from x equals 0 to x equals a of, okay, now y. Here's the thing. Y times a minus a over the square root of b y to the 1/2. What's wrong? What'd I do?
Your differential doesn't match your balance.
Oh, whoop, yep. You're right. That's y equals 0 to y equals b. Thank you. Whoops. All right. You plug and chug that out, and you will get, bless you, you will get ab squared over 10. Okay? If you don't believe me, like, carry it out. Like, it'll be alphabet soup, but you'll get that. Okay? So therefore, so why did I do that? Why are those useful? Like, what am I going to use first moments of area for? What's that? Well, indirectly later, but I'm talking about what property of area will it give us? The centroid, okay? Because I propose that the following is the case. X bar is that first moment divided by the area. So what was the area? Remind me. AB over 3? Is that what it was? So 3 over AB times a squared b over 4. Or 3/4 of a. Y bar is 1 over a times the integral of y dA. So 3 over AB squared over 10, or 3b over 10. See, what I'm getting at is this. What we just determined was the centroid of this shape. Here's the shape. All right? Here's the shape. I propose that the centroid is right here, where if this is A, this is 3a over 4. And if this is B, this is 3b over 10. Pretty straightforward stuff, but pretty nifty. All right? So that's where your first moments of area come into play, is to determine your centroids. And we now know the centroid of this shape. If I 3D printed this shape and put my finger right there, it would balance. It wouldn't tip over, assuming that all the printing was even. There wasn't like a big glob of plastic over there. So that never happens, does it? Any questions? All right. So if you know these, we can set up our moments of inertia. So our moments of inertia are just second moments of area. So if we look at second moments of area, so to determine, let's say, Ix, see this integral up here up top? Times b over a squared x squared dx. Like I'm talking about this integral up here on the top left. The only difference between this and this is that it's the integral of x squared. So when you carry that out, what do you get? AB cubed over 21. Did I have a typo?
Isn't it y for I?
Oh, yes, you're exactly right. You're exactly right. You're exactly right. That's integral of y. Yep. Sorry about that. That's going to become pretty relevant later when we look at parallel axis theorem too. So sorry about that. That's actually, yeah. You can add 0.5 to the mistake counter on my part. Y equals 0, y equals b, and then this is y squared a minus a over the square root of b, y to the 1/2 dy. And so this one comes out to be a cubed b over 5. Yeah, because your moment of inertia, if you're talking about the moment of inertia with respect to the x-axis, you're basically talking about how much area is removed from the x-axis, and so that distance is y. So thank you for pointing that out. That was exactly right. And that's basically it. So if you want to summarize, we have the area is AB over 3. We have x bar is 3a over 4. We have y bar is 3b over 10. We have Ix is a cubed b. Or wait, no. I'm sorry. Hold on. I'm sorry. I have to correct something. Because I got those indices wrong, I got those backwards. This Ix, this is, this Ix, sorry, hold on, I got these backwards. Okay, so the Ix is AB cubed over 21, and the Iy is A cubed B over 5. I apologize for that. That's my fault. My coffee hasn't kicked in. That's what it is. I'm blaming that. 21, and Iy is A cubed B over 5. Sorry about that confusion. That was my fault. If we had carried out those integrals, we wouldn't have had that issue. Okay. Are there any questions so far? I know it's a lot of grunt work and a lot of math. So you want me to leave this up here for a second? I see a couple folks back there writing, so I can wait a little bit. Okay. Oh, I lost my microphone there. All right. I do want to point something out real quick. Like I said, if you go to Appendix E in your textbook, there are values for simple shapes. So let me show you something real quick. I believe I have a PDF of that in my file here. Hold on. Yep, I do. So this should be supplement 2 on the website. So on Blackboard, there's a set of PDFs for lecture notes, and then there's a set for supplements. Am I right? This is supplement number 2, and this is right out of your textbook. This is, I think, out of the last edition of the book, but, I mean, this stuff hasn't changed since, like, the apple fell on Newton's head. Now, one of the things that you're going to notice, I'm pulling this out here. Let me see. I believe that the shape we actually just derived is in there. Now, it's not this number 12 because that's circular. We had a parabola. I'm pretty sure it's in here. Yep, here we go. Well, golly gosh gee, look at that. So the area is, they're using B and H. So they got BH over 3. We have 3B over 4. This was A, or this was A and this was B. So 3B over 4, 3H over 10. We have our BH cubed over 21, HB cubed over 5. So this is all the same thing. A couple things I will point out, just so you're aware. There's a term here that's probably a little new. You're like, well, what's IXY? Okay. Well, how did we do this? This was the integral of y squared. This was the integral of x squared. This is the integral of xy dA. It's called a product of inertia. I don't want to like overburden you. I don't want to like, information overload you right now. But all I'll say is that the product moment of inertia shows up whenever you have sections that are unsymmetrical, that have some weird symmetry, and they're being bent like in a weird way. You can get bending stresses that show up in different directions. We'll cover that later, so I'm not trying to leave. You can use that's a good question. You can use double integrals, and you can use double integration for a lot of this. The reason I don't break out the double integrals right here is because we cover that in Calc 3 here at Marshall, and Calc 2 is the requirement here. So I don't know if you all are in it or not, so that's why I use the single integral approach, because I know everybody knows it. So honestly, like, if everybody in here had already had Calc 3, this problem actually would have gone a little, I don't want to say smoother, but it would have been a lot easier since you can use a double integral approach and it goes a lot faster. It's a little easier set up. So at least I think it is. So.
For those integrals, would it be easier to define a function like y equals h and then just, do the difference between the function that describes the curve and the function that describes that line, and the area would just be the difference between those two?
That's a good question. You're talking about instead of taking the curve, taking like a rectangle and subtracting. Right. The answer is yes. When and we're going to kind of see that in a little bit more of a straightforward fashion when we look at moments of inertia of composite shapes, because the way you determine the moment of inertia of a shape that has, let's say, a hole in it is you treat that as a negative quantity in your sum. So yes, you can. Like if you have an I-beam, you can say that you have 3 shapes, or you can say you have one big rectangle with 2 holes in it, and you can do that too. So yes, but I would say that for this example, that's just too much work. I'm not saying it's not accurate. It's just you're taking this much calculus and turning it into this much calculus for just getting the same answers. So, but it's a good point. Any other questions? All right. There it goes. Are we back? I think we're back. Okay, so I promise in those 20 seconds that YouTube missed, I didn't say what the answer to the exam was or something. When we did the problem in class, we assumed that the coordinate system was right here, whereas what's the difference between this coordinate system and this coordinate system? Well, the difference is that this coordinate system over here on the right is a little special. The coordinate system is placed right on the centroid, okay? Whereas over here on the left, it's actually kind of arbitrary, okay? We put the coordinate system, when we did this problem, we put it right there because it made our calculus easy. But the values that we got for moments of inertia really weren't representative of how the beam is really going to behave. If I bend a beam and it responds by flexing, it doesn't care where you put your x and y axes. You know, it doesn't care. It's just going to respond the way it's going to respond. The way that we resolve this in beam theory is we don't just use regular old moments of inertia. We use centroidal moments of inertia. We use moments of inertia that are referenced by the coordinate systems when they're placed at the centroid, because that does reflect how beams are going to behave. When they bend, you're going to get zero stress to the centroid, and the stresses are going to increase the farther you move away from it. So long story short, if you compute the moment of inertia of a rectangle with the coordinate systems right here at the corner, you're going to get bh cubed over 3. Whereas at the center, you're going to get bh cubed over 12. It's typically a worst case scenario, and it's typically reflective of what's really going on. It's what we use for design. Now, what we do in order to determine that is we can handle it two ways. The first thing that we can do is we can recompute our integrals, which is a very possible option, and in some cases the right way to go. For a rectangle, that's really simple. You can just put your coordinate system there, and instead of integrating from 0 to h, you can integrate from negative h over 2 to positive h over 2, and it's pretty simple. And that's fine for rectangles because the math is really simple. Whereas for that parabolic spandrel we just did, I would argue putting the coordinate system at the centroid, like it's a pain in the butt. Is there a way of determining those moments of inertia with respect to the centroid without having to go through all that crazy calculus? Okay? The answer is yes. And there's two tools that you need. The first tool is Appendix E, because a lot of those properties have already been computed. Why the heck would you go and do a bunch of calculus if it's already been done for you, unless you really like calculus, which if you're like engineering students, most people are like, yeah, that was so 2017. The nice thing about the appendix is those properties are already derived for you, but those properties by themselves only get you so far. In order to compute the moment of inertia of an arbitrary shape with reference to a specific axis, you need what's called the parallel axis theorem. We're running short on time, so unfortunately I don't think I have time to go through the exam stuff with you. We'll probably just have to save that for a later date. My goal is to get it graded for you by Tuesday, but y'all know what's up. So we'll see if I'm here or not, okay? So let's be clear on housekeeping moving forward. Okay, number one, I will try and have the exams graded for you on Tuesday. If we have class and if, what have you, that should be fine. I won't make any promises. Tuesday, your homework will get activated on Blackboard. If we get delayed on lecture topics and whatnot, I have no problem with pushing the homework due date back. I'm not going to say, let's do the 16th with everything going on. I'm not going to do that to you. Next time, we will discuss the parallel axis theorem in depth, because what we did just now was a bunch of calculus. This is I want you to do the calculus because I want you to appreciate what is in the back of Appendix C and how useful it is. What we're going to do next time is do it, what I would say, for real. This is how a real engineer is going to determine these properties, and that's where the parallel axis theorem comes into play, and we'll describe it next time. So I should have exam grades next time. I should have the homework assigned next time. I might be here next time. Or I might have a baby, yeah. So remember, if you see an email from Patrick, that's not spam, okay? So just Pay attention to your email. Unless he's asking you to pay an invoice. All right, that's all I got, guys. I will see you all next week, y'all, or maybe. Have a good, appropriate number of days until I see you. So, all right.